All right, so the question, the brain teaser for today was, um, I'm an odd number. Let me just check somebody in. I'm an odd number, take away one letter and I become even. So a number of you came up with, let me get a bigger font here. Came up with the fact that it's 7. And if you take away the S, it becomes even. And then somebody, which I thought was pretty creative, wrote 11. And if you take away the L, then it's really even. So there's even and there's even. Okay, so that one really didn't work because you end up with the 2 E's. Anyway, I thought that was pretty creative. I didn't thought about that. All right, so first things. Reminder that there's a quiz on Thursday. Okay. I sent an email out about that. I had it at the wrong time, but I corrected the time. But the quiz is on Thursday, not today. And I will try and generally do, I'll try and do quizzes on Thursdays. I think that just came up in discussion. However, on October 22nd, a week from Thursday, I'm going to do the first exam. And this is like a logical breaking point to do the exam. It'll be during the lab session. So Professor Atwood will actually proctor it. So he will give the exam. And it'll cover base units and prefixes. So in other words, you should know that the unit for resistance is the ohm, and we use omega. The unit for current is the ampere, and we use capital A. The unit for voltage is the volt, and we use capital V. The unit for power is watts, and we use capital W. And also convert prefixes. So you'll have to know what we mean by milli, micro, nano, pico, kilo, mega, gigawatt, whatever. So you'll have to know the prefixes. There'll be a couple of problems on conversion between prefixes. 680 ohms is equal to how many kilo ohms? Or 520 megawatts is equal to how many watts? Or converting between prefixes. Then Ohm's law, like we've done problems on, and power, like we've done problems on. So that's the stuff that'll be on the quiz. Okay. I don't do a review session beforehand. As part of the class, because we need class time to get through all the stuff we got to get through. But I am open to doing a review session outside of class time in the afternoon or the evening or whatever. All right, so we can talk about that a little bit later. So that's where we were at in terms of the exam. Okay, so quiz on Thursday. Put that up here. Quiz Thursday. 10:15, and then the exam will be on the 22nd. Any questions on anything up to here?
Mm-mm.
Okay. Whoops. So when we left off last time, we had done a problem like this, and I was trying to get you to see that the 20 volts is not everywhere. The 20 volts is split up, but that wasn't the main point. The main point was to get you to understand that if you're doing a calculation, in this case, I think it was current, we said that you have to use the resistance and the voltage associated with that resistance, not the 20 volts, but I gave you that voltage had a resistance, that resistance had a voltage of 13.6 volts. Then on the next one, you had to use the quantities associated with this resistor. And you were told that the current was 20 milliamps and the voltage was 2 volts, and you were asked to find the resistance and the power, I believe. And then when we got to here, we again had voltage and resistance. We were asked to find current and find power. And that was our lead-in, and we saw that the current in R1 was 20 milliamps, so we had 20 milliamps flowing here. The current in R2 was 20 milliamps, and the current in R3 was 20 milliamps. And that was our lead into series circuits. And that was one of the rules of series circuits. We remember that we said that a series circuit was a circuit in which the current can only have one path. So whatever current, whatever charges leave here, net charges have to go into this resistor. They come out of this resistor, and there's only one place it can go, along this wire into this resistor. And then coming out of this resistor, the only place that the current can go is into this resistor. And then
Professor, we're only seeing the XM page.
oh, yep, okay, let me go back. Thank you.
No problem.
I gotta share. Okay, let me talk about. So in this circuit, what I was saying was you have to use, if you're calculating stuff for a resistor, you have to use the stuff that applies to that resistor. So in this case, the voltage that we were given for the 680 ohm resistor was 13.6 volts. So we use that to find the current. We were given the current and the voltage over here, so we use that to find the resistance.
Professor?
Yes.
But we still can't see nothing.
Are you sure? Because I'm seeing it on my iPad, which is.
I don't see it on my screen.
Is anybody else seeing or not seeing?
Oh, we look like
I can see the series circuit.
All right,
I
so
see the circuit too.
okay, so I don't know who just said that, but you must have something. Check your end that you got video selected.
Okay. I'm gonna try to leave and come back in.
Okay. So, and then when we got to here, we looked at using the voltage and the resistance over here. Okay. All right. So, and that was the lead in into series circuits. And we saw that in the series circuit that, I'm backing up one, the current has only one path in a series circuit. So if I had a circuit like this one, I had a resistor, and then I had another resistor, and maybe a resistor that came down over here, and then went back over here, and then I had a resistor over here, and then I had my source over here. When we look at this, we say, okay, current leaves the battery, goes into the resistors. So far, maybe it's a series circuit. But when we get to here, we see that the current can split. Part can go that way, and part can go that way. So this automatically makes it not a series circuit. We're going to see later on that that's what we call a series parallel circuit. But the fact that I've got a place where the current can split and part go one way, part go another way, that automatically means it's not a series circuit. A series circuit has to have current that comes out of one end of a resistor. The only place it can go is into the next resistor, or in the case of the last resistor, back to the source. All right. So this is definitely not series. Okay.
Question about that diagram, the top left. On the bottom left side, you grounded the circuit.
Yes.
What's the functionality of it?
Well, if I was just wiring this circuit on a breadboard, I wouldn't need to ground it. One of the problems, well, not one of the problems, one of the things we're going to find out is that if we do a circuit analysis program, and I believe did you all get multisim as part of the package for?
Yes.
Yeah, okay, so you got multisim. Multisim requires a circuit ground. So in other words, there has to be a ground within the circuit for multisim to do its calculations. So I just started putting them in to get used to drawing the circuit with the ground. So when you start to put it in, but when you start to put a circuit into multisim, you'll remember that it needs a ground. But just as a straight up, if I was going to take measurements on this circuit, I wouldn't need ground if it was just connected to a power supply on a breadboard. There are other reasons for grounding things. and I'm going to talk in them a little bit later, especially in the olden days, meaning the olden days when we had metal chassis and vacuum tubes and all that other stuff. A lot of times wiring was simplified because the return path back to the source would be via the metal chassis that the circuit was built on. So you would just take the end of a resistor and connect it to a lug that was screwed to the metal chassis. The battery or the power supply, negative of the power supply usually, that would get screwed to the ground. So the return path of the current would be through the metal chassis, saving some wiring. But in today's world, a lot of stuff is on a circuit board. So maybe the ground connection between circuit boards is via the chassis, the metal chassis. But in terms of what we're looking at now, I could have just as easily drawn this without the ground. The other reason I put the ground in is because one of the things we're going to talk about in a couple of minutes is double subscript notation. And I believe that Professor Atwood already mentioned that in lab. At least he said he did in an email to me. But we'll go over it again. And one of the subscripts can be with respect to ground. So long answer, but bottom line is that in this circuit, if I wasn't going to talk about double subscript notation, I really didn't need to put the ground in. Okay, so when we were all done, the last thing we wrapped up with was the rules, and there are going to be some more, but the rules for the series circuit said that the current is the same in each resistor. The voltage across the resistor is different unless, and I left that for a little tease, and the voltage across the resistors add up to the applied voltage. So if I go back over here for a minute, if I add up the 4.4 plus the 2, 4.4 plus the 2 gives me 6.4, plus the 13.6, we come up with 20. Okay, so one of the rules of a series circuit is if I take the individual resistor voltages and add them up, they should add up to the applied voltage. Okay, so let me just take that circuit. I wonder if I can do that. Give me a minute, I'm going to try something. Oh, nice. So if I take the circuit and look at it now, there's a couple of different ways I can reference this. First thing, another rule for Ohm's law or rule in general. We'll talk about the polarity of a voltage. And that has nothing more to do than where do we put the plus and where do we put the minus? All right, because the voltage is going to drop as we go through the circuit. We'll see that in a couple of minutes. So the way to determine it, the end of the component where the current enters.
Sorry, Professor, are you writing this somewhere?
Yeah, I am. I got to change shared screens. Thank you.
No problem. Oh, okay.
Okay, so here's our circuit. I just transferred it to a different whiteboard with today's date. So when we talk about the polarity of a resistor, we're going to look at, say, okay, this voltage, 13.6, was associated with R1. The more positive end of that is on the left side, the more negative end is on the right side. That's not because left is better than right, or it's because when the current leaves here, remember, current always flows from positive of the source through the circuit to the negative of the source. The end that the current enters is the more positive end, and the end where it leaves is the more negative end. So the end of the component where the current enters is the more positive end. And the end of the component where the current leaves is the more negative end. So if I think about, I'll give you a minute to jot down some notes and then I'll talk about it. So if I look at the current direction, the current leaves the positive, it goes into the left end of R1. That makes the left end the more positive end of the voltage across R1. And then as it leaves R1, that makes this the negative end of the voltage for R1. It enters the left end of R2, making that the positive end of the R2 voltage. And it leaves the negative end, leaves the right-hand side of the R2, which makes that the negative end of the voltage. So if we look at point B in the circuit, it's the negative end of the voltage for R1, but the positive end of the voltage for R2. And sometimes it's important that we know where the positive and negative are. So to do that, if I just wrote down this, I have a resistor in a circuit here. Say I got 3 resistors. R1, R2, R3. And I just said to you, the voltage across R2 is 5 volts. Is that plus at the top or plus at the bottom?
Where's the power source?
Oh, good question. There's a power source over here somewhere. Somewhere over here, there's a power source. Between those 2 terminals. So is it plus at the top or plus at the bottom?
On the power source is the plus on the top?
Yeah, another good question. The answer is it depends. In other words, if I didn't tell you about this, the power source, you wouldn't know, is it 5 volts plus minus, or is it 5 volts plus minus? Because if I put the power supply this way, it's going to be the one that's in red. If I put the power supply this way, it's going to be the one that's in blue. And to solve that problem, we go to something called double subscript notation.
One time when I was on multisim, I put the power source upside down and it was not working.
There's a whole bunch of reasons that that could have happened. Most probably because of the way you put ground in. That could be part of the problem. But anyway, I'll come back to that because I could show you that maybe a little bit later. So in double subscript notation, it's exactly what the name implies. Double meaning two, subscript. So I have two subscripts. Okay, so there's two subscripts. And the easiest way to think about it is think about it from a meter viewpoint. All right, from a meter viewpoint, we have two leads on the meter, usually a red and black leads. The red goes to the first subscript. The black goes to the second subscript. From a circuit viewpoint, the polarity shown or the polarity given is the polarity of the first subscript. So for example, in the circuit above, we could write VAB is equal to plus 13.6 volts. Okay, that's saying,
What's A and B?
okay, so we got A, B, C, and ground.
Oh, okay, okay.
Anything along this between components, all of this, anywhere along here is point A. Anything along here is point B. Anything along here is point C. And anything along here is ground. Remember the ground symbol looks like that. So what is this telling us? It's telling you that the amount or the quantity of the voltage is 13.6 volts. So if I didn't have this circuit, I could sit here and I could go, okay, I got this resistor. It's connected between point A and point B. We know that the quantity of voltage is 13.6 volts. And we also know that the plus sign goes with the first subscript, which is A. So that tells me that the plus sign is at the A end of the resistor, and therefore the minus sign would be at the B end of the resistor. If I just wrote V sub R1 equals 13.6 volts, I wouldn't know, is it plus on the left or plus on the right? I'd have to look at the circuit and figure it out. Here I'm telling you two things. I'm telling you the amount of voltage is 13.6, and the more positive end is at the A end. What would happen if I wrote this? What am I telling you with that? VBA equals minus 13.6 volts.
The negative voltage is more at the B end.
So am I telling you something different than I did with VAB equals plus 13.6, or the same thing?
It's the same
It's the
exact thing.
same thing.
It's the same thing. Okay? It's the same thing. And when we get to some of the more the circuit theorems later in the semester, you might be looking at going through a circuit, and you'll have a circuit where instead of going through the circuit this way and hitting the plus side first, you might actually be going through the circuit where you hit the minus side first, and you want to write it this way.
Would that be for like electron flow?
Nope. It's still conventional current flow. But we'll see when we get to superposition and some of the other circuit theories later in the semester, we'll go through a circuit and we may actually hit the negative sign first.
Hmm.
And that'll make sense when we get to it. But what I want you to understand is two things about double subscript notation. You're designating which 2 points in the circuit the component is located, or where the component is located via 2 points. So I'm telling you that this resistor is located between point A and point B. And I'm telling you the quantity of voltage associated with that resistor. And I'm also telling you where the plus sign for that voltage is. So what I'd like you to do is define the voltage across R2 using double subscript. I'm running out of room because all right, so what I'd like you to do is write out, if you were trying to tell somebody about the voltage across R2 using double subscript notation, what would you write?
Right in the chat.
Say again?
We're gonna write this in the chat. Or...
No. We'll go over it. Yeah, well, nah, it's tough because you can't really do subscripts in the chat. So anybody have an idea?
Yeah. Voltage of BC equals positive 2.00.
So what are we saying? We're saying the voltage from point, let me bring this down a little bit so you can see the A and the B. The voltage from point B to point C is 2 volts, which it is, and the positive is at the B end. Okay? It's all making sense? Any questions?
Is it
Okay.
ever,
Say
sorry,
it.
I was just gonna ask, is it ever gonna matter in which like order it is. I know that you were saying that we're going to go through that like later on in the semester, but like, should it usually be just going from like the positive to the negative terminals type thing? So it should always be like BC as opposed to CB, or does it ever really matter?
It depends. When you get to the transistor circuits in next semester, there could be times when you're going in one direction, especially when you're doing the circuit derivations. You may go around the loop in a circuit in one direction or another direction, depending on what you try to do. So I'm going to say categorically, it depends on what
Fair
you.
enough.
Okay. Let me see if I can copy this again and paste it to the next. I'm not lucky. No.
Ooh.
Okay, let me bring that back up again. Let me see if I can reopen it. I think it was because I went outside the edge. That, yeah, sweet. Maybe that lucky. I have to just get this out of my. Okay. Let's share that. Try this again. Okay, I lost a little bit, but that was to be expected. Okay, so we have double subscript notation. So if I wrote down actually, well, let me hold off a minute. So the last voltage we could look at would be V sub R3, which goes between point C and ground. So I could write it as V sub CG, maybe, but what happens if I have a big circuit and there's already a point G in the circuit? So rather than do that, what they do is if the second subscript is omitted, the second subscript is assumed to be ground. And Ronnie, getting back to your question before, that's one of the other reasons why I put ground in the circuit, so I could talk about what happens if we have a voltage with regard to ground. So for R3, we would write VC equals plus 4.4 volts. All right. So the quantity is 4.4 volts. The plus goes with the first subscript, and the omitted second subscript is ground. Which means anywhere along this wire. Everybody with me? Questions?
Mm-mm.
Let's try this. Oh, let me erase that and put that correctly. Um,
Is that 9.1?
yes. Let's see what I got. See if you can do that. Anybody have any ideas?
Mhm.
Give me instructions on how to draw it.
Yes.
Okay.
Well, I guess first, like, you start making like that first vertical line, right? And then you start with the first 4 resistors. So like you have the first 3 going that way horizontally from the vertical line. Yeah. So make 1 resistor, please. And then keep going. And then make
Wait a
another.
minute, wait a minute.
Oh,
What do you want to add in here before? Not even the voltage. What I would say is let's add
the
that
points.
this is point A
Hmm.
and this is point B, right?
Yep. And then keep going. And then make another resistor. And then keep going. And then you're going to be at point C. Make another resistor. Continue the line for a little bit, stop. That's going to be point D. And then from point D, go downwards. And then start another resistor, please. And then go down. And then finish up the circuit, please. Yeah.
Okay. So I forgot to put a plus sign there. So let's put the voltages in now. So,
Oh.
Go ahead.
So the first resistor between point AB is going to be 3.00. And then it's going to be positive to the left and negative to the right. The second resistor is going to be 1.5. Negative to the right, positive to the left. The third one is going to be 9.1. Positives to the left, negative to the right. And then the last one, that's from D to ground, so it's going to be 2.4. And then positive on top, negative on the bottom.
Okay, and the one thing we didn't put in
Is ground.
is ground, which should be in there.
Yeah.
All right, so somebody else have an idea on how we can, that's absolutely right, and I'm going to talk more about that in a minute. Anybody else have an idea about the second part of it? So I got a power source over here.
Yeah.
Somebody else.
Okay.
Somebody else, feel free to jump in.
Not to add it together.
Say again?
Not to add them up together.
Yeah, remember we said the rule for the series circuit was that the individual voltages should be the addition of the individual voltages should add up to the supply voltage. So the easiest way to do that is I want to go from A to ground, right? What I really want, this voltage here that's in here, if I went from here to ground, I would have VA, and that's what I'm looking for. So VA goes from here to ground, but I don't have to go that way. I could go this way. And I could say VA is going to be plus 3 volts, plus 1.5 volts, plus 9.1 volts, plus 2.4 volts. Right? You told me that add them all up. So I'm saying let's add them up and go this way because I have a positive, 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 positive. It reminds me to add. So I could write that as 3.00 volts plus 1.5 volts plus 9.1 volts plus 2.4 volts should work out, if I did my math right, to 16 volts.
Mhm.
So that means that what I've got over here is a power source that's 16 volts, and it's plus 16 volts, which means the plus is at the A end and the minus is at the ground end. Now, putting the plus in over here is redundant because we said way back when that if I have this battery symbol, that the long lead is the plus end and the short lead is the minus end. So just putting in the battery over here told me, well, I would have had, let me back up one. Since I figured out this is plus 16, I need to put the battery in so the long end is at the top and the short end is at the bottom. The long end is at the plus end, which was point A, and the short end is at the other end, the ground end. Questions on any of that, on how I got to there? Yes? No?
You were saying that like when you're looking for the voltage of A, you go all the way from like A and then to B, C, D, and then ground.
Mhm.
You wouldn't go just from A to like ground straight on like that short path.
To the left?
Yeah.
Yeah, but if I had some circuit over here, so imagine that all of this is inside this box. And I
Mm-hmm.
had a terminal over here labeled A, and I had another terminal over here that was labeled ground. And I said to you, okay, what's the voltage from here to here? Outside the box. You got no way of figuring it. You'd have to go inside the box to add all of these up, right?
Okay.
Make sense?
Yes, sir.
Okay, other questions?
Mm-mm.
Anyone else have a question? Feel free to mute yourself and ask. So I have a question. Natasha, you told me how to draw the circuit. But what if I wanted to be obstinate and say, I don't want to draw it that way. I want to draw it.
Oh.
Oops, that got really messy. And let me put some numbers here. R1, R2, R3, R4. Is my circuit wrong?
Mm-mm. I don't think so.
Anyone else think, want to hazard a guess? Circuit wrong or right?
Is right.
Why?
Mm,
One thing you should be aware about in this class is if you answer a question with a yes, no, right, wrong, that kind of answer, it's usually going to be immediately followed up by a why. I want to know what your logic is. So why do you say it's right? You're absolutely right. It is right, but why?
It's
Go ahead.
just it's the same circuit, just a different way.
How do you know they're the same circuit? For somebody who might think it's different, if somebody said to you, I want you to prove to me that it's the same circuit, what would you tell me? You're absolutely right, it is, but why? I mean, what makes you say it's the same circuit?
It has all 4 resistors and the ground and the battery. Just the pattern is different.
Okay, you're on the right track. We got the same 4 resistors. We have the battery, we have ground.
We have the same connections too.
Ah, that's what I was looking for. You have the same connections. If I made up a table and I said R1, R2, R3, R4, and this is the blue circuit, and this is the black circuit. In the blue circuit, R1 connects between A and B. R2 connects between B and C. R3 connects between C and D. And R4 connects between D and ground. If I look at the black circuit, R1 connects between A and B. R2 connects between B and C. R3 connects between C and D. And R4 connects from D to ground. So if I look at it, these match up, these match up, these match up, these match up. If all of the endpoints match up, it has to be the same circuit. And I'm going through that because later on when we get to the next thing we're going to look at after series is parallel, but then when we get to series parallel, there'll be times when you look at a circuit and you can't tell whether 2 components are in series or 2 components are in parallel. If you do what we did over here and say, okay, do they match up or do they not match up? We'll set up a table, not exactly like this, but similar to this, and ask ourselves, do leads match up or not? We'll be able to tell whether they're in series or parallel. So the bottom line here is it doesn't matter which way I draw them. I could have drawn it this way. I could have drawn it resistor here, gone all the way down here, drawn a resistor here, drawn a resistor here, and gone to ground, R1, R2, R3, R4. I could have drawn it that way. And
Where's ground?
ground would be right here. This would be point A. This would be point B. This would be point C. And this would be point D. And that's the exact same circuit as the others. All right. So it doesn't matter what the circuit looks like. Whether I draw it this way, I draw it this way, I draw it this way. It doesn't matter what the circuit looks like as long as all of this stuff matches up. Okay, I have one resistor that goes from A to B, one resistor goes B to C, one goes C to D, one goes D to ground. In each one of those circuits, if you mapped it out, you'd have one that went between A and B. Where A and B is physically on your drawing would be in a different place. I mean, in this drawing, B was to the right of A, and B is still to the right of A, but in this drawing, C was to the right of B, and in this drawing, C is above B. And it doesn't matter because R2 is still connected between B and C, between B and C, between B and C. All right, so how you draw the circuit physically is not relevant to, well, having said that, let me back up. What's important is the electrical connection. Where do the components go? Okay? So that's what I was trying to get across here. I could draw this circuit any way I want, as long as I've got R1 connecting between A and B, R2 connecting between B and C, R3 connecting between C and D, and R4 connecting between D and ground. All right, how I draw it over here doesn't matter, as long as I maintain that AB, BC, CD, D to ground relationship. Okay? Questions up to here?
Can I ask kind of an unrelated question?
Sure. Depends on how unrelated.
I mean, it's not that unrelated. It's just I'm a little. What is ground?
Okay. Ground, in the most technical sense, is exactly what the word says. The dirt outside your house is ground. It's a zero potential point. It's a zero voltage point. There are actually different symbols that are used. This symbol that's shown here is probably one of the most misused symbols in electronics. That symbol says I should be able to trace this point right here, this end of R4. There's a 4 over here. This end of R4, I should be able to trace that through my circuit, out through the power cord ground, all the way out into the dirt. If I can't do that, I shouldn't be using this symbol. All right. But as far as electronics goes, if I take my meter, so here's my meter, I'm going to have a black lead and a red lead. If I take that black lead and connect it to ground, and I took my red lead and brought it over to here, I would measure 2.4 volts.
Okay.
If I took my red lead and connected it to here, I would read 0 volts because I'm along the ground line. If I took my red lead and connected it to here, I would say between this point and ground, I've got 16 volts. I would read 16 volts.
Okay.
And if I went to anywhere else in the circuit, we'd come up with a different number, but I don't want to get into that today because we're going to talk about that next class. But ground you can think about is a 0 volt point in the circuit. So all along this line, I'm at ground. So if I took this black lead and I connected it over here, I'd still measure the 2.4 volts here. I'd still measure the 16 volts here.
Is ground usually closest to like the negative point of the circuit or the negative terminal?
It depends on the circuit. You can't always make that assumption. I can tell you from experience, I was working on a video recorder and ended up connecting to what I thought was ground because it looked like it should have been ground. And I was connecting the ground lead of my oscilloscope, which was grounded through the ground in the power cord. And when this big spark flew off as I tried to make that connection, and then I went back and looked more carefully at the schematic and found out that it was a minus 40 volt or 48 volt high power power supply to feed the videotape motors. That was my wide awakening. Like, you can't always look at something and say, oh, this is ground. Ground isn't always the chassis. And then there was a big note too about it being floating. So
could that have killed you?
Probably not 40 volts, but you know, if I was standing in a puddle and with wet hands and maybe, but it was a big spark and it scared the hell out of me. I'll tell you that much. It made me jump.
Okay, fair enough.
Okay, let's do this. I'm going to knock off a couple minutes early today. So if there are any questions before we do, Yep.
Are we on campus today? Do you know with Atwood?
But Atwood, I have no idea.
Okay.
You have to work among yourselves.
Okay. We are. Okay. I'm getting my car now.
Yeah, we are.
All right. So that'll give you a couple of minutes to get there too. All right.
Okay. Thank you.
See y'all on Thursday.
Okay.
Ready
Bye.
for the quiz.
Yeah. Okay. Bye.
Bye.